what? 3 into 10 power minus 6. Bus? Should be something like 3.6 maybe. Okay. So I will do that question. So we are continuing our discussion on wave optics, and this is lecture number 3. And I want to discuss that homework question. Again, a very simple question. What was the question? Can somebody give me the question? Because in YDSC, you have to find the thickness of a glass slab. Its mu is given, which should be placed in front of an upper slit so that the central maxima now lies at the fifth bright fringe. Yes, before the experiment. So you have something like this, and you have two slits. Yes, and now what is happening is there will be a central maxima here, and there will be a fifth maxima here, fifth bright fringe. And what is the distance of fifth bright fringe from this? It's y5, na? Yes. And what is y5 equal to? What is yn equal to for any maxima? Position of nth maxima? That's n lambda d by d. Yn is n lambda capital D by small d. That means y5 is 5 lambda capital D by small d. This is the position of fifth bright fringe before doing anything. Now what you do is you put your slab here, and when you do so, a shift occurs, a shift in the position of the central maxima. The central maxima gets and goes there, gets shifted to that position. And do you know the shift ka formula? The shift is equal to what? Mu minus 1 into T capital D by small d. This is the shift. Na? Now your shift has to be equal to this y5. Yes or no? So that means this mu minus 1 T capital D by small d has to be equal to 5 lambda capital D by small d. And then you can find the thickness very easily. What is the thickness equal to? 5 lambda by mu minus 1. What is mu minus 1? That's 0.5. What is lambda? 5 into 10 power minus 7.
10 meters.
5 into 10 power minus 10. यही है क्या? Minus 7. Is there any problem here? It's correct. And now this 0.5 can be written as 1 by 2 goes there, becomes 10. So this will be 5 into 10 power minus 6 then. है ना? 5 into 10 power minus 6 meters. So maybe I was saying another thing. This is what I am finding. Did you get the same result? ठीक है. So for those who did not try the homework question, copy. Otherwise I am just going forward. We had one, I have done one question in the board na last time. कोई भी नहीं किया था. अच्छा, wait. By the way, we are doing very extremely easy questions right now. But after the end of discussion of all of it, you remember na, the last time I did, I gave you a sheet and then we did some good questions. We'll do the same again. I'll give you the sheet after the whole discussion and then we will do some good questions. For now, these are just introductory questions, simple questions. ठीक है. Let me write another question so you attempt that. Okay, attempt. I am giving you 3 minutes. Again, an extremely easy question. Then we can go forward. There's still a discussion of this resonance tube is remaining, and leave some space after this question. I will write 3 lines of note, but not today. So not even 3 lines, give 7-8 lines space, and then we will start with the discussion of diffraction. वो notes में बाद में discuss कर लूँगा, okay? But remind me कि ये 2 चीज़ें करना है. Incorrect. कितना? Incorrect. Incorrect. वैल्यूज देख लूँ मैं एक बार. यस वैल्यूज. अच्छा मैंने वेवलेंथ लिखा है. वेवलेंथ लिखा है, सही है, ठीक है. आंसर 3.6 10 पावर -5. ठीक है, करेक्ट. Anybody else with the answer? -3 what? ठीक है. Should I start? It's very simple. It's a single formula question. If you remember the number of fringes shifted, I gave you a direct formula for this. What was the formula? Mu minus 1 into t divided by lambda, na? And no. This is the number of fringes shifted. This is the formula, and that is given to be 30 fringe shifts. So mu minus 1, that's 1.5 minus 1, and you have to find t, and lambda is given to be 6 × 10 power minus 5 centimeter. The 1.5 minus 1 0.5 goes there. 60 into 6 360 into 10 power minus 5 3.6 10 power minus 4 ना नहीं -3. Is it okay? सेंटीमीटर. ये तो बहुत सिंपल ही क्वेश्चन था. तो we will do some good questions later on, but I am moving on with the topic. Is it okay with everyone? So we will start with the topic of diffraction. But before even diffraction, I have to introduce this idea of wave fronts.
We have to be leaving half of it.
Leave at least 10 lines. 10 lines or something like this. Half page, it's okay. Now things will get a little messy, and I have been struggling for 2 classes, so please listen carefully. And if you listen carefully, sab samjhega. But if you are somewhere other than here in your mind, then kuch nahi samjhega phir. Huygens बताऊंगा अभी. What is the meaning of wave fronts and why are we talking about this? So you understand this, that the idea of rays was not good enough. I will tell you why. By example, by simple drawing, we will be able to understand why idea of rays are not good enough. That's okay. But anyways, we said that waves are much more better, and we used to think that everything is in terms of waves and it's all good. But to actually make diagrams using waves is a little difficult to imagine. That's why we will try to introduce this new idea of wave front, which is basically the wave. Everything is the same as the wave, but it's much more easier to imagine. And what is a wave front? So I will give the definition here. But before even that, let me give you some example and then let me try to talk about it. Let's say you have a point source. I have a point source like this. What will the point source do? It will give off waves in all possible directions. Yes? So it will give off waves in all possible directions. All the points or all the waves which were coming from the point source at that instant t equal to 0, they were all in phase. Yes? They all move with the same speed. Then after some time t, they will cover the same distance. Yes or no? So if I were to be tracking this point which has traveled some time, after some time t, it has come here. Then if I talk about the same point at the same time, it will come here. What is the phase between these 2 points? Phase difference.
0.
There's no phase difference because they are basically moving together. Yes or no? They are moving together and there is no phase difference, there is no path difference between these 2 points. Can I likewise find many points like this? And if I take all these points and join them, what will I get? Circle. But in reality, what will I get? A sphere. Yes or no? A sphere like this. Then instead of imagining waves, what we will try to imagine is this surface. This surface which has a peculiar feature, and the feature is that the phase difference between any 2 points on the surface is 0. Then such a surface is called a wave front, and this is an example of a spherical wave front. So this is a spherical wave front. Yes? And what is the definition of a wave front? A surface for which all the points on the surface are in phase, or you can say for any 2 points on this surface, the phase difference delta phi is equal to 0. That is a definition of a wave front, and this here is a spherical wave front. Everyone has written till here? If I take an example of a tube light, maybe which will act like a line source of light. This is a line source of light, a tube light, not a point source but a line source. Then can you imagine that on this is my tube light or maybe some line source, all these points, they will give off light rays outwards, yes, and if I connect all these points, what will I get? A circle. And if I stack circle on circles, what will I get? A cylinder. So what kind of wavefront do you hope to get here? A cylindrical wavefront. Do you understand the meaning? Where all the points on the curved surface area of the cylinder has the same phase. They are in phase. So let me make the diagram. Hopefully you will be able to imagine this. This is a circle. Likewise you will get something here as well. This is my cylindrical wavefront. Is it okay? A cylindrical wavefront. And now if I talk about a point source where the point source is very far away, let's say. This is my point source. And from this point source, what kind of wavefront comes out? Spherical wavefront comes out. Comes out like this, moves forward, and then let me talk about this part of it. Keeps on growing, na? And now for a person who is standing here, very very far away, what will this part of this, what he will see, the part of it, what will it look like? A line? Think in 3D. What will it look like? You will see a patch of a football. Yes or no? The football keeps on growing and what you are seeing is a patch of the football. Are you understanding? A plane. अभी भी नहीं समझ आ रहा है. अरे how will it be curved? You are going very very far away. Since this is a huge football, and now this is a, ये ऐसा है ना, ये patch है. You take a very very small element. What will it look like? It's a patch, yes or no? And this is what you will see. So what you will see is a plane. Then such a wavefront is called a plane wavefront. A plane wavefront. Do you understand? So a spherical wavefront can be thought of as a plane wavefront when the distance between the source and the observer is approximately infinity or very huge. Then all the wavefronts that are coming out of the sun, we will consider them to be plane. Do you understand? And please understand, we have not abandoned the point of view of waves. It's still the same thing. We are just taking another structure and trying to imagine. Wavefront उसको नाम दे दिए. Do you get it? Yes?
Yes.
It's all good? So this is the idea of wavefront. Why did I introduce this? Because Huygens principle actually directly deals with wavefronts. And why are we even talking about Huygens principle or even wavefronts? Because when we talk about diffraction later in the lecture, we will use that idea and the whole picture will become very intuitive. Everything will become very very simple. So let me write it. It's done till here, na? So the Huygens principle. Huygens was a guy, and actually the point of view that he came about with this wavefront idea, That was not really there initially. I think in 1600s or something like that, Newton gave the idea of corpuscular theory, where he said that light is made up of little particles, and he called them corpuscles. And the idea is totally rigged actually. Why? Because if you take that point of view, you will never get the results that we find experimentally. That's why corpuscular theory fails miserably. It's only after 200 years or so that somebody actually came and actually said that Newton is wrong, and you have to take another point of view, the point of view of waves, not particles. And Huygens gave the idea. And then he further extended to wave fronts, just for simplicity. So let me write the principles.
So for 200 years, they will
Uh-huh.
For 200 years, they will
One idea is,
For 200 years, they will
for 200 years nobody was able to object it. कोई साइंस जायंट के सामने ऑब्जेक्ट करना कि तुम्हारा आइडिया रॉन्ग है एंड देन गिव अ काउंटर एग्जांपल इज अ ह्यूज थिंग. That's why not for 400 years, 1600, for something around 400 or 450 years nobody questioned relativity, and then Einstein said ki no, it's all wrong, the whole idea is wrong of Newton. The time is not absolute. Anyways, first principle. Let me look at it and then write it so that I don't mess up. I will write one thing that will be helpful to you to imagine. So, ये कहाँ गया? The first, I will write the principles, then I will explain later. So please write with me. Every point don't irritate me. I'm going to write dx and that's directions. Huh? This is the first principle, and the second principle is once you're done with it, then tell me.
What is it, sir? Secondary
Wavelet. I will talk about all of it. Just try it for now. Is it done? Is it done? Great. So what is the first principle talking about? Let's say you have a source, a point source. Gives off waves in all possible directions, huh? And then it gives off a spherical wavefront. Let's say this is my spherical wavefront. Just for simplicity, I'm making a circle right now. Then what is the first principle saying? The first principle is saying that this is going to be called a primary wavefront. Huh? That all the points on the primary wavefront acts as a source themselves, and if they act like a point source themselves, then they will give out wavefront in all possible directions themselves. So they will create little wavefront themselves. Yes or no? So it will be something like this. Something like this. They will give off light in all possible directions themselves. They are acting like a point source. This is the first principle, nothing more. And all of these waves obviously move with the same speed of light as the original wave. The second principle is saying, now you have these tangents, the forward tangents. Look at this. Do you have a tangent here like this? Here like this? Here like this? You connect all these tangents, and if you connect all these tangents, what will you get then? You will get the wavefront at a later time. It seems very obvious, why are we even writing this? But these two statements themselves are very powerful. We will try to explain diffraction and even interference that we have already talked about using these statements. So and this is called a secondary wavefront. Now it's obvious that the secondary wavefront will itself act like a primary wavefront later. All the points will act like a point source, and then it gives off, and then you can keep on doing it again and again. Yes.
प्राइमरी वेवफ्रंट के ऊपर जो पॉइंट्स है वो फिर से
वो सोर्स के हिसाब से एक्ट करेंगे. This is just a point of view. Obviously, there is only one source. These are not actual sources, but Huygens thought of it like that, and then he said, if I do take this point of view, then what happens? Then can we actually explain physical phenomena? We'll try to do it. Okay? Wavelets. यही है बस, ये जो हमारा जो वेव फ्रंट बन रहा है ना इन बिटवीन, वही वेवलेट है मान लो. Is it okay? We will use this principle extensively. Most of the time in interference and diffraction, but अब interference हो चुका है तो diffraction में ही, but I will still give you an understanding of why this is so good. For imagination. Remember, waves गए नहीं है कहीं पर. They are still waves. They are physically actually the correct thing. Wavefronts are just for our simplicity to imagine. Do you understand? Good. Why did we use rays पहले? Because that was simplicity to do calculations. So it's for our own क्या बोलते हैं benefit or convenience. Is it done? Now let me give you two pictures and based on that let me make some results, and then you will hopefully get an idea कि why this wavefront का idea is so better. Let's say कि I have a double slit experiment again. I have a double slit experiment, and let's take the point of view of Newton. Just for fun, why not? Let's take the point of view that light is made up of little discrete particles, and instead of particles, let me make, for simplicity even, I will take ping pong balls or anything, rocks. You can throw anything, just material particles. You throw it. When you throw it, when you're standing in front of this opening, you can throw more and more, na? And when you are at some angle, तो can you imagine कि वो opening actually थोड़ा कम दिखती है, and the probability of going the particle in that way is much more lesser. So, and by the way, what is the intensity defined for particles? What is the intensity defined to be for particles? For particles, what is the intensity meaning in terms of particles? I have written this as well. That is the number of particles crossing per unit area. That is the meaning of intensity. Meaning of intensity in the point of view of particles is how many particles did actually pass. है ना? So let's see. I am going to make the intensity pattern. What do you think it should be? So there will be more and more particles passing through this directly, and less particles at some angle. So it should be something like this, na? If I were to make this thing, ये क्या हो रहा है? If I were to make the diagram, shouldn't it be something like this? There should be two maximas, a minima here, because obviously no particle will go in this region, it's blocked. And what about here? It's also blocked. तो अगर मैं balls फेंकूंगा तो एक ऐसे distribution दिखना चाहिए ना? Yes or no? This is my intensity distribution. Intensity as a function of y. This is my y, na? Yes or no? Where you only get two peaks for two slits and nothing else. Everywhere else is just, there's nothing. If you take the point of view of you are throwing particles, okay? If you take the point of view of you have rays, then rays actually travel in straight lines, na? Yes or no? They travel in straight line. If I have a source here placed here, then most of the rays will just pass directly. Maybe some of them will hit here and then go like this, some of them will hit here and go like this, but बस उससे ज़्यादा नहीं होने वाला. Most of the rays will just pass directly. Yes or no? What should the intensity distribution will look like then? Exactly like this. Maxima in front of the slit and then nothing as you go away. Yes or no? So what should you hope to get? Even from here you will get the same thing. Two maximas and rest all minima. Is this what we get in reality? When you have two slits and two sources placed in front of it? Is this what we get? What was the pattern that we found last time? Same. There was a central bright fringe and there were many fringes, not only two. If you remember, there were a lot of fringes and the actual pattern was something like this. Keeps on going on. Isn't this the pattern that we had? Are there only two maximas in this pattern? No. Then should I take the point of view that light is made up of particles as Newton said? That doesn't give me interference pattern. Should I take the ray ka point of view? That's not giving me either. That what point of view is correct? Let's take the point of view of wave fronts, and that's basically waves, na? If I take the point of view of wave fronts, तो फिर कैसा होता है? अब मैं तुम लोग को एक एनिमेशन भी दिखाऊंगा. But before that, let's try to understand this. What will happen? Let's say you have a point source here. यहाँ से waves ऐसे आई. Yes, the waves will come here in this small opening. ये small opening में. What will the points act like? All the points on the wavefront acts like a source themselves. They give off waves in themselves. So all of these points will act like a source, gives off waves, and then you consider the common tangent. है ना? And the waves will come out like this. This is through one opening, but we had two openings. Huh? Let me make the other opening, and if I take the other opening, then what will you get? Then there are waves which are coming out like this. Bolo, are they meeting at different points? They are superposing at different points, and based on whether they are in phase or out of phase, you will get a destructive or a constructive interference. Are they meeting only at 2 points? No. ये तो बहुत जगह. और उसके बाद स्क्रीन पे क्या दिखेगा? इसका पैटर्न दिखेगा. Yes or no? You can imagine it as if you have a pond and then you drop 2 stones or 2 pebbles. You get some kind of pattern like this, na? Ripples through this. And can you see that the point of view of wavefront makes everything so simple to imagine? है ना? It's so natural that there should be an interference pattern because you are interfering at so many points. It's not only in front of the slit, but at so many points. It spreads out, doesn't it? That's why we will use it. So I did not introduce this idea of wavefront last time or when I started with interference, but this is the correct idea to imagine.
If we go to that Newton's
Bolo. You had particles now.
So in the particles, what if the particles are reflecting back, like after they fall on the screen and they reflect, so that it falls?
You are just leaving it like this. It will stay like that. You are saying it will bounce off like that. No.
It bounces and then keeps on.
नहीं ये सब कुछ नहीं.
Sir,
बोलो.
what if the particles collide with each other and then move to different parallel lines?
Yes, that can happen. That's why I did not put a distribution like this, where there is a maxima in the just a maxima concentrated. I spread it out a little bit. It is a little spread out. No? There is a possibility that the particles will go maybe at some angles, but that's it. The maximum intensity will just be in front of the slit, and you will get a pattern like this. Is that the correct pattern? No, right? Good. So hopefully the idea of wavefront is clear with everyone. You don't have to write these diagrams or anything, but is the idea clear to you? Why are we using wavefronts? Good. Now let's talk about diffraction. Waves collide नहीं करते बेटे. Waves meet करते एक point पे, they may superpose. बोलो आगे.
मतलब वो इंटरेस्ट हो रहा है.
हाँ
वो कैसा हो रहा है?
कैसा हो रहा है का मतलब क्या होता है? सुपरपोजिशन फॉलो कर रहे हैं ना. दे आर बेसिकली वेव्स. वेव्स सोचो उन्हें, वेव फ्रंट बनाया मैंने, वेव्स हैं वो. इज द आइडिया क्लियर टू यू? मैं एट द एंड एक एनिमेशन दिखा दूंगा, ठीक है? क्या बात क्यों होने लगी अचानक से? Can I go on with the idea of diffraction? Now, have you seen this? कि I don't know if you have a peephole in your home के door के ऊपर, but वो रहता है ना जिससे you will be able to see, or something like this. Or even if you have a little opening, or if you have a simplest experiment would be if you have a cotton wala handkerchief and there are small pores inside it, and then you see the sun. वो small pores क्या है? Circular like this, ना? If the sunlight is actually in the terms of rays, then the sunlight should just pass like this, and you should just see an intense beam of light to you. But what do you see? It spreads. Yes or no? Doesn't it spread? Even for a headlight that is coming from far away, do you see a beam of light or it spreads? It spreads. So if I have,
If we keep close to it, it looks like a sharp.
yes, if you are close, मैं अभी बता रहा हूँ, सब बता रहा हूँ. There are some conditions why it spreads. अब अगर एक ये देखो, if I have an aperture like this, it's just a small circular opening, and then you have some kind of candle in behind it. So what do you think should happen? Agar if I take the point of view of rays, then the rays which are passing parallelly ऐसे बस दिख जाने चाहिए. तो वो इधर मुझे क्या दिखना चाहिए? बस intense circular circle which is there, and rest all will be shadow, na? Yes or no? Rest all will be shadow, and you should just see a patch of circle that is from the beam of light. Yes or no? But what do we see? We see actually a little spreading. Yes or no? There's actually even a little intensity here, and the circle, and as it goes away, it fades away. So bending, there's a bending of light that is occurring here, right? There's a bending of light, and the bending of light is called diffraction. So let me give you another diagram. And another diagram could be that you have an obstacle here, an obstacle like this, with a sharp edge. And you will understand why I am saying sharp edge later. Let's say you have a source of light here. This is my obstacle, and this is my screen. What do you think should happen? If I am going to put my source just behind the obstacle, it only makes sense that itna to shadow hona chahiye na? Itna shadow region hona chahiye? This is called the geometrical shadow region. Geometrical shadow region. And what you should find is the light that is coming out, that will only go here. But what do you find? Do you find some kind of light here as well? You do. वहाँ पे भी थोड़ा सा light आता है. That is due to bending. So let me show it. Goes there. क्या होता जा रहा है? Goes there, and actually a little bending occurs. This is the bending of light. Why does it occur? Why should it occur? If I were to take the point of view of this, क्या नाम है? Wavefront, then let's see is it natural or not that it occurs. कि I have the same diagram again. I have a sharp edge, and the edge is like this, and now my source of light gives off wavefronts. Wavefronts come here. Then what happens? Each line on the wavefront acts like a source, gives off waves in all possible directions. Will it only give off waves like this? No, obviously not. It will give off waves like this. Yes or no? Then you will obviously find some kind of intensity. Maybe the intensity is very small because it's a little, most of the light actually passes, only some part of it bends. So you will still find some kind of light here, na? Even in the geometrical shadow region. Bending of light or spreading of light in the geometrical shadow region is called diffraction. And do you see that by the point of view of wavefronts is so natural that it should be true? Why should it be like कि only part of it is going up? It spreads out all in all directions, huh? So it's true. So this is diffraction. So you don't have to make the other diagram. बोलो.
On the bending of light area.
Shadow form. ये जहाँ पर है ना लाइट, यहाँ पे थोड़ी सी इंटेंसिटी दिखेगी, ज़्यादा नहीं, बट थोड़ा सा दिखेगा. Does it make sense to you?
Sir,
So let me write it below.
in that yellow color light region in the geometrical shadow region, does it produce light or a shadow?
Light on a, it's not like there was a shadow always. ठीक है, there was nothing here, there would be a shadow, but it's our normal sense that there shouldn't be any kind of light that is coming here. That's why it's called geometrical shadow. If you take the point of view of rays, that's geometrical optics. नाम थोड़ा ऐसा लगना चाहिए. Geometrically ऐसा दिखता है ना कि ये ब्लॉक कर देगा पूरी लाइट, बट ये ब्लॉक नहीं कर पा रहा है ना.
A little light is coming.
Yes, there it does come there, and that's called diffraction, bending of light. बोलो.
So diffraction is basically bending of light in terms of phase, and diffraction is bending of light in terms of phase.
It's all waves. It's all waves. ये तो मैंने बस दिखाने के लिए बोल दिया. It's all waves. As you can see, the diagram that I made for wave fronts, that was the correct diagram. Actually, this is just for your understanding or your imagination. अगर बनाना है तो फिर मैं वो भी बना देता हूँ, और उसके बाद वही बना लो तुम लोग. ठीक है, वो 2 पॉइंट लेके मैंने बस बता दिया. बट ऑब्वियसली देर आर सो मेनी इनफाइनाइट पॉइंट्स. बेंडिंग ऑफ लाइट, सो दिस इज क्या बोलते हैं यार, स्प्रेडिंग ऑफ लाइट in the geometrical shadow region is called diffraction.
So this phenomenon is only for light or any kind of wave?
For water waves even it does occur.
Not for all waves generally.
For all waves I think it should occur, but ठीक है, मैं देख के बताऊंगा. I shouldn't say a statement which I am not comfortable in or sure in. ठीक है. Is this okay? Is the idea clear to everyone? This is diffraction. Now I was going to say something. क्या बोलने वाला था? Yes, I should say this. This is a important note. That I am going to write a statement which is what you will find in most of the books. Not correct actually, but still I will write it because it is what is written in your books. Okay, then I will give you the correct statement. The statement is that the diffraction is not seen through all the holes or all the possible apertures that you can think of. If you have a huge aperture through which the light can go, then do you see a significant amount of diffraction or bending? No, most of the light will just pass through the directly, and इतना bending होएगा ही नहीं. The bending of this light is apparent only if you take a very small enough aperture, and the size of the aperture के ऊपर एक condition है. That's the condition of diffraction, and the condition is that the size of aperture should be of the order of the wavelength of the light. So condition of diffraction is that size of aperture should be of order of wavelength of light. This is the statement. But now as soon as I write this statement, the thing that should come to your mind is that ये आदित्य को चुप कराओ कोई. Go and sit at the last bench. The thing that should come to your mind is that wavelength of light is in the nanometers, angstroms. That's 10 power minus 10. How small? Do you have such openings that are that small? And only then do you find diffraction? Obviously not. Then this statement is not that correct then. The correct statement should be the size of the sharp edge should be of the order of wavelength. And what do you mean by sharp edge? ये जो मैं दिखा रहा हूँ ना ये जो दिखा रहा हूँ ना ये edge, इसका sharpness should be of the order of wavelength. That is the correct statement. So I am writing it. But वो एग्जाम में तुम लोग ये लिख के आना, ठीक है? Should be if that sharpness is of that order, then you will find a diffraction. This is the condition. I'm not proving this condition right now, I'm just giving it to you. Remember this, okay?
Sir, but the length of that aperture does not matter, right?
It does matter actually.
It is like a phenomenon. Maybe the intensity of that light beam decreases or increases, but the phenomenon will occur naturally.
It does occur, but not that prominent. Bending will occur, but if you have, let's say you have some kind of light beam बोल रहा हूँ ना, beam यानी कि समझो कि most of the light is going like this, and then you have a circle like this, an opening like this, then most of them will just pass through directly. कोई bending हो रहा है क्या?
But
नहीं
an
है.
example of straight like a rod kind of thing.
हाँ, एक और एग्जांपल मैं लेके बता सकता हूँ where this bending won't be that apparent or maybe not occur at all. एक लेज़र लाइट लो. लेज़र क्या है? मोस्ट ऑफ द लाइट इज कॉन्ग्रेगेटेड इन वन बीम. अब उसको एक बिग इनफ ओपनिंग से पास करो, उसमें कहीं होएगा बेंडिंग? नहीं होने वाला.
But that is
अगर वो एरिया को छोटा करते गया तो प्रॉबेबली हो जाएगा कहीं ना कहीं. क्या चीज़? हाँ, अगर वैसा करोगे देन, अगर तुम वैसा कर रहे हो then it's basically talking, you are increasing basically the wavelength. You are making the wavelength to be of the aperture size in a way. Anyways, is this condition okay with everyone? We'll try to use it. And acha, before even doing the narrow slit ka derivation, I have to give you the types of diffraction. We will only talk about one of the types. So that is the Fraunhofer one. So let me first write it. Types of diffraction. The first one is called the Fresnel diffraction. अभी इधर से ही पूरा confusion start होएगा, तो बहुत ध्यान से सुनना, ओके? Fresnel diffraction. And the other is Fraunhofer diffraction. Most of the time, or basically all the time, we will only talk about Fraunhofer. Okay, we will not talk about Fresnel, but I am just introducing the thing. What is the meaning of Fresnel diffraction? It's all about the distance of your screen and the source. If that is a finite distance, then you will say that the diffraction that is occurring is a Fresnel diffraction. So let me write it. If Fresnel diffraction. And if it is very close or maybe finite, then if you take a point source, what kind of wavefronts will you get? What kind of wavefronts? Spherical wavefronts. Spherical wavefronts. If I talk about the Fraunhofer, then here it's just the opposite of it. The distance between the source and the screen is at infinite large distances. So an example could be light ray or light which is coming from sun. It's at a huge distance from Earth, na? Then that distance we can approximate it to infinity, and then we will say that the distance is huge. The distance between source and screen is infinitely large.
So this plane wavefront is like
Huh?
plane wavefront.
That will be found here, right? So that will be plane wavefronts. Is that okay with everyone? Now I am going to make a diagram, and this is what we will keep on doing. I said कि rays are not good for us because rays do not give the correct calculations, right? But if you remember, it was much more simpler to deal with rays because they are basically lines, and then it's much more simple to do mathematical calculation. So even though I said कि rays are not that good enough, but we will keep on using rays again and again. ठीक है? And I will keep on switching between ray का diagram and wavefront का diagram. And then you have to keep on imagining between this and that. अब वो सही से नहीं हुआ तो फिर सब कचरा. ठीक है? And this is where सब लोग परेशान हो रहे हैं, तो hopefully you will get it. अच्छा, let me tell you, ask you this, कि if you have a situation where rays are coming from infinity and I want to mimic this situation at a finite distance as well, then what should I use?
Keep the intensity low.
No, what I am saying is I have a situation where, what is this situation? Distance between source and screen is infinitely large. So the wavefronts or the waves or the light is coming from infinity. I want to mimic this situation at a finite distance. What should I use?
Smaller versions of those.
Smaller and bigger, like largest.
What should I use? Big, कुछ भी बोलता है. What will help me to mimic the situation of as if the light rays are coming from infinity?
A parallel beam of light.
How will you create such a thing?
Two laser rays.
अरे बेटे, a convex lens. You put a source in front of a convex lens, maybe at the focus, and the rays which will come out are like parallel rays, and that will mimic the situation as if they are coming from infinity. Yes or no? So if you want to do this thing here,
And we can also project a parallel beam of light from a torch.
कहाँ से parallel beam of light लाओगे?
From a torch maybe.
टॉर्च में से पैरेलल बीम ऑफ लाइट नहीं निकलती, स्प्रेड आउट होता है बेटा वो. आई वॉन्ट टोटली पैरेलल. ये भी तो पॉइंट सोर्स क्या करेगा? स्प्रेड आउट करेगा. एंड फिर इसमें से क्या निकलने वाला है? ऐसा ना कुछ. एंड देन इट विल कम आउट लाइक दिस. अब देखो, अब समझो, when the light rays, when they come here, let's even leave rays. When light encounters this small opening, what happens?
Some particles get refracted.
अरे refracted कुछ नहीं. अभी क्या पढ़ाया? When your light actually hits a small opening, what happens?
Refraction.
What is that?
Pendulum
बेंडिंग, देयर विल बी बेंडिंग. सो ये रेज जो है, ये रेज बेंड हो जाएंगे थोड़ा, होंगे कि नहीं होंगे? दे विल गेट सबटेंडेड एट सम एंगल. तो मैं एक सिर्फ एग्जांपल दिखा रहा हूँ, ये बेंड होंगे ऐसे. समझ आ रहा है? अब ये ज़रूरी नहीं है ये इधर ही बेंड, ये ऐसा भी बेंड होंगे ना. यस, हाँ सब बेंड होंगे बेटे. बीच में कुछ भी नहीं है. हाँ ये वाला पास, चलो ठीक है. चलो मैं सिर्फ दो के लिए बताता हूँ. ये दो बेंड हो जाएंगे, ठीक है. बस अब उतना पकड़ो. You put another convex lens here and then they will get converged and this is what you find in screen. Is it okay? Is it okay with you? Good. Why are we putting another convex lens then? Just so that they meet at least. And do you understand the whole situation is by very artificial. We are doing this, all of this, but if you were to take natural sources and take the point of view of wave fronts, then all of it occurs naturally. Yes? Good. अब मुझे ये बताओ, diffraction में will there be a superposition? So if you remember what was happening for interference, you had openings like this. Actually, you had openings like this, wave fronts were coming, and what was happening? ये हो रहा था ना, ये हो रहा था. If you look carefully, then actually if I take this opening ऐसा कुछ, even if I don't take the other part, still diffraction होएगा ना. And diffraction is what? बेंडिंग ऑफ लाइट. तो ऐसा आएगा एक की वजह से भी. सो इफ आई लुक एट इट, देन इसके वजह से एक रेज आ रही है एक्चुअली, एंड इसकी वजह से दूसरा एक वेव फ्रंट आ रहा है, एंड इनका फाइनल इफेक्ट ये मैं दिखा रहा हूँ इधर. समझ रहे हैं? बट इन दोनों की वजह से भी देर आर सम काइंड ऑफ सुपरपोजिशंस दैट यू सी हियर, दैट इज ऑल्सो अकरिंग हियर. Do you understand? So even in interference there is diffraction occurring, और जो final thing दिखता है वो एक दूसरे का superposition दिखता है. Final thing. Are you understanding? So even if I take a single slit, there will still be superpositions. अब वो तुम लोग ये मत बोलना, ये this is what happened in other class, that if I have a screen, ये ऐसे opening, तो बस एक ही तो बस निकलेगा, एंड देन सुपरपोजिशन कहाँ हो रहा है, एंड हाउ डू यू गेट अ पैटर्न? बिकॉज आई विल गेट अ पैटर्न लेटर, बट पैटर्न कब आता है? व्हेन देयर आर ऐसे मीट करते हैं ना कहीं पर, फिर डिस्ट्रक्टिव कंस्ट्रक्टिव कुछ होता है, फिर यू गेट अ पैटर्न, राइट? इफ यू टेक दिस पॉइंट ऑफ व्यू तो नहीं होएगा. तुम लोग को ये समझना है कि इधर ये हो रहा है. वो मैं फाइनल इमेज बना रहा हूँ. व्हाट इज हैपनिंग इज दिस, यहाँ पर भी डिफ्रैक्शन, यहाँ पर भी डिफ्रैक्शन, एंड दोज मीट्स. समझ आ रहा है? इसके वजह से वी विल फाइंड अ पैटर्न. आर यू ओके विद दैट? वी विल फाइंड वन पैटर्न हियर. गुड. तो ये डिफ्रैक्शन का एक पैटर्न आएगा. गुड. सो नाउ वी आर इक्विप्ड विथ एवरीथिंग. नाउ आई विल टॉक अबाउट, we will only talk about one single case. Actually it's very limited, but there can be many cases. There can be a case where you have an aperture, circular aperture, and then diffraction occurs. We will not talk about that. There can be a case where you have only single क्या बोलते हैं, एक ही ऑब्जेक्ट, सिर्फ एक ऑब्जेक्ट, nothing else, still you will find diffraction as we have seen. We will not talk about that either. We'll talk about the simplest case, a single slit. Before we were talking about two slits, ना? Now we will talk about a single slit, और single slit से diffraction pattern देखेंगे. तो Fraunhofer diffraction through a narrow single slit. Hopefully you are writing with me.
So the example that we took on the right is merging of both the kinds of interactions.
The interference.
This Fresnel interaction and Fraunhofer interaction, we are merging those two in one single case, and that is the example of that case.
No.
Like we are creating.
Fresnel is for finite distances.
The distance is finite, and at the same time we are mimicking the situation.
This thing are you talking about? No, this is an example of Fraunhofer. Why? Because we have finite, but we are final. ये final thing infinite जैसे दिख रही है ना? ये infinite जैसे, बस इसको इसी को देखो और कुछ देखो ही मत तुम. ठीक है?
The condition is that the light source
Should be at infinity. Should be at infinity. Are you okay with this? Now let's talk about this one. Let's say I have something like this. Now obviously I am exaggerating, इतना तो slit width होना भी नहीं चाहिए, but let's say this is तो ये A है, slit opening का length, and then you have a screen like here. What? ये जो ये बनाया वो कुछ भी नहीं है, वो छोड़ दो, वो तो बस उसको दिखा रहा था कि वो प्लेन. ठीक है, वो बनाना मत. ठीक है. You have rays of light which are parallel. You can even imagine कि यहाँ से plane wavefronts are coming, since it's a Fraunhofer ना, plane wavefronts are coming, and then what will happen? यहाँ पे spherical wavefronts comes out. यहाँ से भी ऐसा. Are you okay with this? This is the true diagram. For simplicity, I will make another diagram just for the calculation part. I will make this diagram. अरे यार. Now obviously I am taking the point of view of rays ना, ठीक है? ये ऐसे है. Is it okay with you? What is the slit width? That's A, and let's say कि from the center line what is it? Let's say this is making some angle theta, this is capital D, and the point at which I am talking about is small y. Yes? The point at which, who is this talking? क्या मैं पलट के देखता हूँ तो सब चुप हो जाते हैं, कौन है ये बात कर रहे हैं? एक तो इतने मेहनत से लेक्चर लो, सोने नहीं होता क्या तुम लोग? सो जाओ, 2 घंटा सो जाओ, बात मत करो मेरे लेक्चर में, समझे? नहीं तो आने का ही नहीं क्लास में, फिर घर पे बैठो. This is angle theta, and if you remember, I made a right angle triangle last time as well. This is my right angle triangle, and this is A by 2, let's say. From the center line, if that was A, then from the center line that's A by 2. Then if I take any two rays and try to find their path difference, then that is the path difference between them, na? If I take the small, this is what we have done even in interference, if you remember. It's exactly the same treatment. Now what was, if this was D and that was theta, then we found it to be D sine theta. Now it's A by 2, that's theta, so what should it be? A by 2 sine theta. So what should be the path difference? So delta x is A by 2 sine theta. Okay, A by 2 sine theta between two rays. If this A by 2 sine theta, this path difference is equal to lambda by 2, then will you find a constructive or a destructive interference? Come, both of you come. हाँ, जल्दी जल्दी. If I take lambda by 2, then ये constructive होएगा या destructive होएगा? The part difference is lambda by 2. Come on यार, इतना simple question नहीं बता पा रहे. Constructive. ये क्या, ये ऐड हो जाएंगे ये लोग, ये सब्ट्रैक्ट होंगे. क्या आंसर आएगा इसका? ये डिस्ट्रक्टिव है या कंस्ट्रक्टिव है? कितना है पार्ट डिफरेंस इसमें? So if I take delta x to be lambda by 2, that's a condition of destructive interference. So if I take a by 2 is equal to a by 2 sine theta as lambda by 2, that's basically writing a by 2 this, then you will get a sine theta is equal to lambda. Now it's very interesting, this is the condition of dark fringe, by the way. So I'm erasing this. This is the condition of dark fringe. If you actually look at it very carefully, in interference we used to find this condition that d sine theta is equal to n lambda, and then we used to say this is the condition of constructive interference, where if you had an integral multiple of lambda, you were finding constructive interference. But what about now? That's destructive if you have an integral multiple of lambda. This is 1 lambda, na? You can do many variations and you will get this general condition. The general condition is a sine theta is equal to m lambda. And it's actually exactly opposite to interference. In interference there was n lambda pe constructive, now here it is destructive. This is also the condition of this. Do you understand this? What will be the position of the mth dark fringe? Position of mth dark fringe. If you remember, we used to do it by assuming that sine theta is approximately tan theta, and tan theta is equal to y by d. And then we used to write ki ym is equal to m lambda by a. This is the position of mth dark fringe. Sometimes they also ask you what is the angular position of mth dark fringe. Then the angular position is the angle subtended from the center line. What is this ym? This is the distance subtended or distance from the center line. Na? What could be the angle subtended? It's very simple. You just substitute sine theta approximately theta under the small angle approximation, and if sine theta is theta, then what do you get? Yes, since sine theta, so here theta m, that's the angle subtended for the mth dark fringe, that's m lambda by a, and obviously everything is in radians, remember. So this is the angular position. Do you understand whatever we did? I am only writing for dark fringes right now, but these are the calculations. What will be the intensity function? If you remember, I think we derived the intensity function when we were talking about this interference. Huh? I don't remember. Did I derive it or did I give you directly? I think I derived it, na? I equal to I1 plus I2, I took that and then I found the final form. I'm not doing that right now. The actual derivation of intensity of a single slit experiment, that's far beyond your syllabus right now. So I'm just giving you the final form, the function, and based on that we will try to see. So is it done till here? अभी आखिर में कितना टाइम बाकी है? लिखो लिखो मेरे साथ जल्दी जल्दी. Intensity distribution function, and the function comes out like this: I is equal to I naught sine beta by 2 by beta by 2 the whole square. Somebody write somewhere that I have to discuss 3 nodes: resonance tube, and the difference between diffraction and interference. I also have to talk about that. I think ये आज नहीं हो पाएगा. ये बीटा is not a fringe width था. I should write this alpha. ये alpha लिख लो. And anyways, the alpha by 2 is pi a sine theta by lambda. I'm not teaching more than this for today. But this is the intensity distribution function that we have. I will try to talk about more things afterwards. You can actually go at home and then try to make this on Desmos and then see what kind of function do you find. And based on that we will go forward. Okay? So you can switch off the video.